Right now, as you're watching this, somewhere in the world is actually uploading a video. And for the next 60 seconds, 500 more would have uploaded video. 500 minutes of video every single minute forever. And the wild part, you can just choose any video and press play on it. It will just play. No please wait, no buffering, it just works. So here is the question, how on earth would you actually design a system like this? If someone walks up to you and asks, how do you design YouTube? Where would you even start? That's what we are doing today. From a blank page to a fully distributed system, by the end of this video, you will walk into the system design interview and confidently sketch this in the whiteboard. Let's get into it. Before we draw a single box on the board, we have to understand the scale of this problem. Because YouTube just isn't a system, it's an exabyte scale beast. And the numbers are honestly a little ridiculous. YouTube has around 2.7 billion monthly active users, more than 100 billion daily active users, 1 billion hours are watched every single day. By the time you have watched this video, about 15,000 hours of new video will have shown up in the YouTube doorstep. We're not building that today. That would take weeks. We're building a system that handles around 100 million daily active users. YouTube shaped, but not full YouTube. Same problem, same architecture, but scaled down numbers. Honestly, if you can build for 100 million daily active users, it can easily scale up for 2.7 billion. Now, before we dive into functional requirements, there is something most tutorials skip. This is the part where people actually trip up in interviews. You can't design YouTube if you don't understand video. That sounds obvious, right? But watch. Most people walk in thinking, I'll just store the video and I'll send it to the user whenever they ask. Then the interviewer asks, what happens if a slow 3G user wants to watch a video? That's when the entire problem falls apart. Three concepts. Once you have these three, the rest of the design feels almost obvious. First, encoding. Let's say you're shooting a video on iPhone. Someone else is shooting a video on Android. Someone else is shooting a video on fancy camera. So there are three different formats, three different codecs. If YouTube decides to store the raw files, then the clients have to handle three different formats. It's a nightmare. There are a number of formats of videos. So the first thing YouTube does is transcode it, meaning it takes the format you upload and it converts to a common format across all the videos. So this way, the client only handles couple of formats like H264 or BP9. Those are wrapped in a container, for example MP4, but it doesn't just stop there. YouTube produces multiple versions of the same video, like 480p at 1 megabytes per second, 720p 2.5, 1080p 5 megabits, and 4K 15 megabits per second. These are stored independently, and remember, they're created once but reused every time someone watches a video. Second concept, adaptive bitrate. Picture this. Let's say you're watching a video on YouTube and you enter into lift. So the network just drops. If YouTube is sending you 1080p video, even if your bandwidth is not good, then you will see buffering. So YouTube uses something called as adaptive bitrate. It adapts your video quality based on your bandwidth. If your network drops for a bit, it will change to 720p. If it drops more, it will change to 480p. And if it backs up, then it climbs up till 1080p. That's why you wouldn't see buffering much in YouTube. This is how it actually is resolved. So the next one is the multi-part upload. Let's say you're a YouTuber, you have recorded 1 GB of the video and you want to upload in YouTube. So if you upload the entire 1 GB as a single file, what happens if the upload fails at around 80%? The upload have to be restarted from the beginning. So here we use multi-part upload. The client will divide the 1 GB video into multiple parts and each part is uploaded independently. We can parallelize them, meaning we can upload more than one part at a single time. So if a part fails, then we just restart the single part instead of the entire file. So the flow goes like this. The client will send the entire file size and the backend will return the multiple URLs, which is called multi-part URLs for a blob storage like S3, and client will use those independent URLs to upload each part. After that, each part is transcoded and encoded for a seamless experience. Here comes the functional requirements. Now that we understood basic concepts of video and uploading, let's dive right into the scoping of the problem. So as part of the current design, I'm planning to implement these 5 features. Uploading videos, that is very essential in YouTube, and search and discover, that is also essential. If you want to watch a video or search a video, you'll need to search it. Then stream videos, yeah, this is also essential if you want to watch a video. Then like and engage and view tracking, these are optional, but I chose to put it in the system. But you can talk with your interviewer and finalize if they are looking for the features or not. So let them know what you're thinking and finalize the requirements. And also I've mentioned out of scope features. I just mentioned recommendation, subscriptions, live streaming, monetization. You can talk with your interviewer that I'm considering this as out of scope. If we get time, we can come back later and implement more features. So the next step is to scope non-functional requirements. So as part of the system design, I'm planning to have these as non-functional requirements. High availability, obviously we need high availability of our system so that system keeps running and we get and we as a business get money. And partition tolerance, as YouTube is a very huge system, and as we have already discussed, many videos are uploaded every second. So we want to have partition tolerance where we can distribute the database. Then eventual consistency, this applies per feature. Like for some part of the system, eventual consistency is not applied. For example, you're uploading a video and you added metadata, and when you go to your profile, you should be able to see the metadata you have added for video. That's where the strong consistency applies. And let's say you liked a video and the other person across the world doesn't need to view your like or comment instantly, so it can eventually add it to the system. This is where we make the trade-off for eventual consistency for likes, comments and views. Then adaptive delivery, as we have already discussed, we need it to be supported for lower bandwidths. Then low latency search, as we are supporting search, we want the search application to be less than 500 milliseconds. Now comes the back of the envelope calculations. So this is not something out of the box. Just try to talk with your interviewer and just try to get the hold of the scale, which helps you to assume the databases, blob storage, S3 and all those stuff. As part of the current design, I'm planning to have these as back of the envelope calculations. For storage, we are considering 720,000 videos per day, as we have discussed, 100 million uploads. If we generalize for a minute, we'll get around 500 videos per minute. Then let's say each video is 1 hour long and at the rate of 2 Mbps on an average for all the qualities, which would be around 900 MB after encoding for a single video. Then we'll also have multiple bitrate like 480p, 720p, 1080p. If we multiply 900 into 3, we'll get around 2.7 GB per video. If we multiply 2.7 GB per 720,000 videos per day, we'll get around 1.9 petabyte per day. That's a huge storage. You don't have to mention the accurate calculations, just a round off, just an assumption to get a scale on the mind. So next, the throughput and bandwidth. This is optional if you are aiming for staff level or senior level interviews. This is very important for you to mention that. So here, let's say we have 1 billion hours per day videos being watched. If we want to have concurrent users per second, we'll have to divide by 24 hours, then again 3600 per second. Then we also have per stream bitrate, meaning for per every user, for every time they are watching, we'll be having around 2 Mbps across all quality levels. Then total egress bandwidth from the perspective of your backend, where your backend is trying to stream your videos to multiple users, 12 million concurrent streams, and each concurrent stream around 2 Mbps, which comes around 24 TBs per second. Upload throughput, we have 720k videos per day, which when we divide it with 86,400 seconds, which are for day, we'll get around 8 videos per second. So not high, would say. You only have to support 8 videos per second, which is around 7 Gbps ingress. where the backend is trying to get the ingress traffic. Then API queries per second. Here APIs are for other services like searching or logging, commenting, likes and stuff. For 100 million daily active users, let's consider 10 API calls are being made for every day. We want to have per second queries. When we divide it with 86,400, we'll get around 12k queries per second. Now that we have functional requirements, non-functional requirements, we have a hold of back of the envelope calculations. Now we want to design the entities, where the entities are just actors in a system. So for this system, we have user as an actor, then video is an entity, video, which is what we store in the database. Video chunk is also an entity where each video will have multiple video chunks. Then we also have like and comment. For simplicity, I've considered it as a single entity, but you can mention as a different entities. So this is entity relationship model. You don't have to draw the entire diagram in 45 minutes of the interview. Just let the interviewer know that each user can upload multiple videos, so you have one-to-many relationships there, and each video have multiple chunks. You also have one-to-many relationships between video and video chunks, and each user can like multiple videos. So user to like is a one-to-many kind of relationship. So this is how you would specify the relationship model. Then the next step is the API design. Now that you have entities set up, so you are going to design the API design where you can refer to those entities in your API design. As part of the functional requirements, remember, try to make one-to-one relationship with the functional requirements and the APIs you're trying to create. Let's say the first feature is the upload. We have upload APIs. There are two APIs. One is the videos initiate upload, and the second one is the videos complete upload. So the initiate upload, what it does is that it takes the size of the actual file user is trying to upload, and backend decides the part size, each single part size, and it also returns the pre-signed URLs. This is a new concept. I'll try to explain what is a pre-signed URL. So if you are uploading a part of the video, you don't want to keep your backend as a means of transport to store the file, which is in S3. Let's say S3 as an blob storage to store the video. Blob storages like S3 gives you an opportunity to send a pre-signed URL which is valid for a bit of time, like 1 hour, 2 hours, which the client can use directly to upload the video in S3. So when you use that, your backend doesn't need to scale for so many video uploads. Your client directly talks to S3, and your backend can be linked to the S3 to find if a part is uploaded or not. As and when the client completes the upload, the client also calls the complete upload to finalize all the paths. At that point, backend will verify all the paths are uploaded to S3. So the next API is search endpoint, get video /search, and user will send a query, and backend will search for the videos and return the video entity that will have the entire title and description, which you can look in the YouTube page. You don't need to watch the video, so you will not get the streaming URLs. So when you click a video, that's when the other call for get videos video ID will be called, where it will return all the metadata for that video and the streaming URL as well. The streaming URL I will try to explain in further design. The streaming URL we are using CDN as the streaming, so that CDN streaming URL is written by your backend. Then an API to post a like, delete a like, and post a comment and delete a comment and stuff. So now that you have APIs set up, let's start with the system design architecture. So we'll start with the client. We have a client which can be browser or a desktop or a mobile or a tablet. Irrespective of the client, we have a single client, and that client will talk with an API gateway. Why do we have an API gateway here? So like YouTube is a bigger service, it's a large scale service. We want each service to be independent. Here we'll be using microservices architecture. you can speak with the interviewer. You can let them know that as the scale is huge, I'm going to go with microservices architecture from the beginning. If your interviewer wants you to not have microservices architecture, and if he asks you to design a monolith architecture, you can also go with that. Then you would not have API gateway. So here we have an API gateway which will also act as like a rate limiter for us. It will also handle authentication for us as well. So from API gateway, we have multiple services. So here we are using, let's say, Kubernetes or the ECS Fargate, where there are multiple instances of each service. You can't have a single instance of a service right after the API gateway because of so much scale. So here we have three replicas of the upload service, and three replicas are preceded with a load balancer, which will be contacted by the API gateway. So here we are doing horizontal scaling. So we have upload service, we have search service, we have video service, and we have engagement service, bifurcating each functionality. When you're going to talk about the upload flow, here we have a client, a single client, and an API gateway. And clients want to upload a video. The first API is the initiate upload. So the client will call the initiate upload, which will go to the upload service. And what upload service does, it stores the upload metadata in the metadata database. Here we are considering a SQL database here, for instance. If you think NoSQL database makes more sense, try to talk with your interviewer and let them know that why you are thinking in such a way. So here it stores the metadata, and it also returns the pre-signed URLs for a predefined set of paths. It doesn't need to send the pre-signed URLs for all paths. Let's say we have a 1 GB video, and each path is 100 MB. You will have 10 paths, right? Maybe around 11-12 paths. So the upload service doesn't need to send all the 12 pre-signed URLs, because it takes time to create the pre-signed URL from the S3, because it needs to talk through an API. Let's say it returns 5 pre-signed URLs. Client will start uploading the paths directly to the S3 using that pre-signed URL. And as this is the starting of the upload service. So then from then on, each part is uploaded to S3. Now we want to do the encoding and transcoding. How do we do? Does your client calls the encoding service, or is there something else? So here we are using S3 notifications. So for every video or for every change done in S3, there is a configuration which you can enable, after which S3 will call an external service triggering for every change done in the S3. If we integrate S3 with the SQS or SNS, where for every part uploaded, that will trigger an event, and there are services like encoding and transcoding service and consolidation service. What is consolidation service? I'll try to explain further. So now encoding and transcoding service, it looks at, okay, there is a new part uploaded, now we have to do the encoding and transcoding. It pulls in the message, it consumes the message, and it does the encoding and transcoding, and it stores back in S3. Again, the encoded part is uploaded to S3, and it also communicates with the metadata DB to actually store that metadata. Then the consolidation service. What is consolidation service? So for the first time, when the upload is initiated, the metadata doesn't have the information for every part uploaded. Why? Because we are using pre-signed URLs which directly called from client, and your backend or your metadata database doesn't have an idea whether a particular part is uploaded or not. So here we would use the same SQS event to update the status of a particular part. So if your metadata DB is up to date for each part, if your upload in the client fails and they try to reload, you don't need to upload the same part, because the parting mechanism doesn't change, and you can have each part hash stored in your metadata, and if a part is already stored, you can just skip uploading that part. So how does your metadata database is actually updated? Here the consolidation service is actually consuming each part upload and updating your metadata by finding that entry and changing that to uploaded to true. So like I said, encoding and transcoding also updates your metadata database. So now that is one flow from the S3. There is also a complete upload API being called from the UI, just to be sure that client saying, okay, all the chunks are uploaded for a particular video, and I'm completing the upload, verify it. So the complete upload will again go to the upload service, and it updates all the metadatas for each chunk, and it also verifies whether each chunk is actually uploaded or not, because client can claim that all the parts are uploaded, but maybe some part is lost in between. So the backend will verify whether all the chunks are uploaded, and it will return the response. Then there is the search part. So here we are using Elasticsearch as the search database. It is not a source of truth, but Elasticsearch is used for search kind of scenarios, and it is very fast and in-memory search backed by Lucene indexes. Every time users want to search, that search request will go to the Elasticsearch, and we have to make Elasticsearch up to date with the new uploads being done in metadata database. How do you do that? So for metadata database, if we are using SQL database or NoSQL database, we are using CDC, change data capture. So change data capture is like a triggered by the metadata database. So every time metadata is uploaded, it will trigger a CDC event, and that CDC event is consumed by the Elasticsearch, and Elasticsearch gets updated with the latest data powering the search. Then we have CDN for streaming. So we have video service, but we cannot support so many videos streaming parallelly. There are CDNs available like Cloudflare, or there are other CDNs as well. Cloudflare is the famous CDN used for streaming videos or storing files, which are geographically used. So every time a video is uploaded, it can be stored in CDN, and the client can directly talk with the CDN for the streaming. So here we have a video service. So when the user wants to watch a video, they'll click on the video. That request go to the video service, and video service will get a streaming URL from the CDN and returns the streaming URL. So then client will directly connect to the CDN saying, okay, I want to watch a particular video, and CDN will take care of streaming all the parts of the videos directly from the S3. So here you don't have your backend service getting stuck for each streaming we are supporting. So CDN will directly connect to the S3. If CDN doesn't have the latest video, it fetch it from the S3 and stores it in the CDN cache. When someone else asks for the same video, it is directly streamed from the CDN instead of going to the S3 every time. So this is the final design, where we have clients, API gateway, we have three services: upload, search, video service, and we have a CDN cache, and we have metadata database, we have Elasticsearch for powering search, and we have S3 for blob storage, and SQS, which is set for the upload events coming from S3, and a consolidation service which actually does updates each part, whether it is uploaded or not. Then there is encoding and transcoding service, which gets triggered for every part which is uploaded in SQS, which directly connects to metadata DB, and after transcoding and encoding, it uploads to S3 directly. And we have metadata and Elasticsearch connected with the help of CDC. So this is how each part of the service will look like. So that's all. You have designed YouTube. So this should be a good enough design for SD2 and senior levels. I'll also try to show you the actual Excalibur diagram which I've done, which is the exact one-to-one replica of what I've drawn in my system design interview. So this is the design which I've done in the interview. So we have, which is exactly like the illustration which I've given. So this is more of the complete design, how it looks when you actually draw in Excalibur. So we have two clients, S3, load balancer, before service. You don't have to draw a load balancer for each service. Just let them know that there is a load balancer and you can horizontally scale each service, which saves you some time for drawing each part of the design. And we have search service, video service, pass through metadata cache. So I wanted skipped the cache, but you could actually have a cache here. So let's say there is a video which is very popular in internet and people are actually watching the video across the world. So instead of going to the metadata DB for every for all the metadata for a particular video, you can have a pass-through metadata cache which can be reused for famous videos if it is being watched a lot of times. So here CDN cache is specific for your video streaming, but not for the data. You can have metadata cache for just the metadata. And yeah, I think I have covered most of the parts, which should be good enough design for SD2 and senior levels. This is what I've answered and I've got the offer from the company. So yeah, that's all for designing YouTube, and please subscribe for the next videos.